You're listening to Useful Science Podcast, produced in collaboration with the Moorhead Planetarium and Science Center. This week we're talking about physics and teaching complicated concepts. Useful Science is the website where we post one-sentence summaries of scientific research relevant to your everyday life. On this podcast, we bring on a rotating panel of our science contributors to pick out a few items from the Useful Science archives and dive deep into them. So while the website gives you the short tweetable version of scientific research, our goal here is to give you the full story. Let's meet our hosts for this week.
My name is Duncan Bell, and I work in science education here in Sydney, Australia. I hold a Bachelor of Science from the University of New South Wales.
Hi, I'm Jaime Devine. I am an operational fatigue and performance scientist in Baltimore, Maryland. I have a PhD in neuroscience from Brandeis University and a certificate in sleep medicine from Harvard Medical School.
Hi, I'm Avaneesh. I'm currently pursuing a PhD in theoretical physics at UCSD, University of California, San Diego. And I mostly do research on how different species of bacteria can coexist together under limited nutrients.
And my name is Cameron Spencer. I'm not a scientist. I'm a web developer and a web designer, and I work on the Useful Science website. So, Duncan, this is sort of a crossover episode with your podcast, Physics Twist. Can you tell us a little bit about that?
Absolutely. So Physics Twist is a podcast that I started for the company that I work for here in Australia, which is called Physics Education. It's spelled Fizzics because we think we're funny, but we're not. And originally it started off as a sort of science and technology news podcast that I host with a colleague of mine. And we've actually pivoted fairly recently to do a little bit more in-depth topics, and it's aligned with the science curriculum here in Australia.
Well, what is physics education? Physics. I see. Oh, I get it. It's physics, like physics.
Yeah. It's a terrible pun. So what we do is we're a science outreach company. So what we do is we go around to different schools, probably hundreds, if not thousands, every year, and we do these really awesome science stage shows and workshops with kids. So we might get up on stage and, throw up some fireballs and play with liquid nitrogen and all that sort of fun stuff. And the idea is that, yes, all those shows and workshops tie into the syllabus, so kids can actually learn really, really, relevant and interesting stuff through fantastic demonstrations. That's what we do.
We have a similar company here in America called Mad Scientist.
Oh, yeah.
And I think there's a few others, but I worked for Mad Scientist for a short period of time.
Oh, fantastic.
It was... The kits they gave us were sometimes underwhelming, but you could tell, like some people were really good at doing a science stage show, and some people were really bad at it.
Yeah.
And it's so cool because you think about what you need to teach people, whether they're adults or whether they're children. Sometimes it's very different. And so, some adults who weren't engaging to other adults worked great teaching these concepts to kids. And you realize oh, you're better at this based on the audience. And it is really important to get across to those audiences.
Yeah, definitely. It's something that I found as well. And people that I work with might be, really good with certain ages of kids. Like they might be great with kids aged, say, 5 to 7. Personally, I'm better with kids because we only do primary school, so up to year 6 mostly. I'm better with the kids who are, say, year 4, 5, 6, so like 10, 11, 12, just because I find them, you can talk to them like they're almost adults. So that's the age that works for me, but yeah, everyone's different.
All right, well, let's dive in then. So Duncan, why don't we talk about your article?
Awesome. So I chose a topic that's near and dear to my heart, which is science communication and science education itself. And it's an article that came out really recently, actually only a couple of days ago, about the effectiveness of using virtual reality as a method for teaching physics concepts. So what they effectively are doing is testing how students, which I think in this were aged between 18 and 24, how they learn a particularly tricky topic using a hands-on activity versus sort of a virtual desktop simulation versus using virtual reality. So in their introduction, they note that technology is obviously now really pervasive in classrooms. I see this all the time, as things are a little bit different from when I was a lad. So you see smart boards, which are interactive digital whiteboards. They're in schools all over the place. Personally, I don't think they're very good, but they are there. And then you've got laptops and iPads. They're fairly common as well, I think, but they tend to be in schools which are a bit more wealthy. But yes, obviously technology is becoming more and more pervasive in schools all the time, and in universities, obviously. So a few educational technologies have not really managed to demonstrate any measurable gains in student learning, which tells us that the technology itself is not that important, but how and why it's used actually is. The authors give the example that interactive lecture demonstrations have found measurable learning gains when students are actively engaged in making predictions and explaining observations from the demonstrations, whereas things like instructional labs using the same or similar equipment don't show the same benefits. So I think really, there, it's about making sure that there's actually cognitive engagement in what they're actually trying to learn. If you're just doing pure instruction, you're less likely to get that engagement. The authors also explain this concept of cognitive embodiment, which, well, I'll quote what they say or wherever they've pulled it from. The mind must be understood in the context of its relationship to a physical body that interacts with the world. Apparently, researchers have found that learning benefits from hands-on activities because it helps to shift understanding from abstract to concrete. I think this is a fairly similar concept to kinesthetic learning, if you guys have heard about that. Think about it in terms of some concepts are just best learned through physical interaction with a model or equipment. So, for example, like you couldn't learn to ride a bike by listening to a dusty lecturer. You have to go and actually do it. But VR might be a useful stepping stone to getting there. The authors also explain difficulties in learning because of real-world complexity. So in a real-world experiment, students can have a really difficult time grasping what's actually happening, of measuring and observing effects because of the uncertainties introduced by the real world. So these uncertainties increase what they call the extraneous cognitive load. And Jaime, maybe you'll have something to say about that as a neuroscientist, perhaps. So extraneous cognitive load is, you can think about that as being information that's irrelevant for learning. So that impedes the learning. So as a simple example, like imagine that you're trying to run an experiment that tests the flight time of some paper planes to find the best one. You might run into a lot of uncertainty in doing that. So, that person didn't fold the plane right, that person can't throw, that person cheated, there was a gust of wind at the time, that sort of stuff. And reducing those uncertainties, which obviously will add a lot of extraneous cognitive load, would be quite difficult and time-consuming. Whereas hands-on activities will involve guiding the student to reduce uncertainty, which reduces the extraneous cognitive load and hopefully improves learning. But those are not always successful. So simulations remove the real-world complexity almost entirely, but they're quite low on that embodied cognition compared to hands-on experiences. Now, the question then is, why test VR, right? And the idea is that VR can reduce the extraneous cognitive load found in real-world hands-on activities whilst allowing for the embodied cognition that simulations can't provide. So what they did in this study is, it was a between subjects experiment, 3 conditions. One is using a VR headset, one's an interactive desktop simulation, and the third is an analog hands-on activity. There was 172 participants, all aged from 18 to 24, 138 women, 31 men, and 3 other. And each condition has basically the same design. It's a Sun, Earth, Moon system where the participant can control time and observe the changes in position of the Sun, Earth, and Moon. And what they're doing is they're trying to teach the phases of the moon. So in, for example, the VR experience, the participants' motion is tracked and they can move through time using these button presses. You know how they have those little remotes that you can hold? So you can move through time by pressing the buttons on those remotes, or you can actually go and grab the moon and move through its orbit. The desktop simulation is similar. It uses the same sort of game engine to run, but rather than using those remotes, they would just press arrow keys to move through time, and you can look around using the mouse. In the hands-on experience, though, the participant's head represented the Earth, and the moon's represented by a small ball that they hold out at arm's length, and the sun is represented by a stationary light. So what they did is they assessed learning with pre and post tests. So you obviously do a test beforehand to gauge your knowledge of how the phases of the moon work. Then you go through these one of these conditions, and then they test you again to see if you've learned anything. And the test consisted of 14 multiple choice questions about the moon phases and the moon's motion relative to the Earth. And the participants were also asked their gender, their video game experience, their VR experience, their academic major, and their environmental attitudes. And this part's a very important part, which is that after doing the post-test, students were also allowed to try the other two conditions and were then asked which modality they preferred. Does all of that make sense?
Mm-hmm.
Yeah.
Awesome. So, the results. The interesting part. There was no significant difference in post-test results across the three conditions, meaning that the researchers were not able to show that VR is a more effective method of teaching. But the students did prefer using VR.
So were they quizzed, quizzed on the subject matter to see how much they actually learned? And that was
exactly
what was being compared. Okay,
exactly. And the increases and the average results across all three conditions pretty much exactly the same, or at least we should say that there's no significant difference between them. So what do we make of this? Well, one thing that they noted is that the gender and video game experience were highly correlated, and men performed better in the VR condition. So the authors say that this means that either video game experience, being male, or a combination of the two provides an advantage. But I think this is really interesting. One thing that we should definitely note is that the study was funded by Oculus Education, who make VR equipment, although the authors note that Oculus had no other involvement in the study. However, I wonder if they're happy about this result. I'm guessing.
So you're
not.
saying that gender and experience of video games was correlated. So
Yes.
Men in the study tended to have more experience with video games, and
Precisely.
those people also did better with the VR simulations, but it's not clear if it's because of the video game experience or because of the gender or because of both.
Exactly right. Yeah.
Each other. Okay, got it.
So when I read this, one of the things that shouted out to me was how much they pushed the idea that VR was more engaging and that lots of students would prefer to do VR, which makes sense now that Duncan has talked about the funding source. But it kind of seemed counter productive to me, because I think the reason why a lot of people would want to go for the VR experience is because of the novelty.
Precisely.
But at the same time, the novelty is the reason that there is a lot of cognitive load on your learning performance. And thus, for people for whom there is a higher cognitive load, that is the people who do not have a lot of experience with video games, you do not have as much of a benefit from in the learning perspective. So I feel like you can get engagement, but it'll be at the cost of actually benefiting. And so when I saw it, I was like, okay, that's not really helpful.
Yeah, I think you've absolutely nailed it. And then the authors do note that learning VR is a lot of extraneous cognitive load, and many of the participants would have been trying it for the first time. So their domain cognitive load, which is the load that's actually relevant to their learning, would be therefore limited.
Well, can we also talk about they have 138 women and 31 men. So you really can't compare those groups. Mm-hmm. And if they were finding that men who, the men in the study had more experience with video games, it could be that if they had an equal number of men and women, or if they had only done this with, like a gamer subgroup or a male heavy group, they might have found more significant differences. So it seems like they didn't really balance gender in this study. Mm-hmm. So I find it a bit awkward that they're trying to explain how gender might have a role. Because 31 men versus 138 women, you can't treat that like a balanced group.
Yeah, they do say they have enough statistical power to do these analyses. I didn't check that for myself, but and I don't think they're really trying to explain these results as a result of gender. They're saying, look, the amount of video game experience and gender are correlated, and we can draw our own conclusions about that. But it's still really interesting, I think. One thing I was thinking, though, and I want to get your thoughts on this, is I think moon phases might not be the best task to demonstrate, the capacity for VR to effectively teach. My girlfriend told me about a similar study that had been looking at learning surgical techniques. And I thought, okay, that'd be interesting because it's a bit more, it involves a lot higher cognitive load, but it turns out that showed similar results. So I'm wondering if you guys could think of any concepts that might benefit from learning in VR.
I was thinking about that, and on one hand, you could think of things that you could be teaching that would not benefit at all, like if you were teaching long division. Doing that in VR doesn't seem like that's going to help at all. But then I was thinking about an animation class I took in college and learning about parallax effects. The idea that if you're animating and you have things, if you're in motion, if the viewing angle is in motion, that things in the foreground will be moving across the screen faster than things in the background because of parallax. And if you're in a 3D environment and you can shift your head back and forth and actually see those parallax effects happening, then I could see how that would help. That would help people understand that concept.
For sure. Yeah.
Yeah.
I wonder, though, do you think you could have the same amount of learning from just doing the same thing in a virtual desktop environment where you move around with the mouse?
Maybe so. I think maybe the surgery is a better example because it's like a highly detailed 3D space that you need to understand.
Yeah, and that's where the concept of embodied cognition comes in. But again, like they said, apparently there was similar results there where VR did not provide additional benefits. It's really interesting.
I actually thought that the moon phase idea was very well suited for VR because, I'm used to learning a lot of things on the screen, and thus VR, in some sense, one of the biggest advantages would be going to 3 dimensions. So having something like the moon phases where the 3-dimensionality of it actually makes a huge impact, I thought would be beneficial. And also, regarding Cameron's examples, I think those examples I would have actually preferred just doing a hands-on experiment, so where you can demonstrate parallax by running or by moving around. I don't know if where VR would, one of the things that seems VR can be helpful is when you cannot replicate something hands-on and you need something like VR to show the sun and the moon and the earth.
Yeah, for sure.
Well, I think that might be the downfall for moon phases, because we exist on the earth, we revolve around the sun, and we look up at the moon and we see the moon change. So in many ways, we're experiencing that in a very real way every day we exist on earth. So that seems like a concept that might not need to be replicated in a 3D environment because we're already doing it. Whether it's your head is the earth and this ball is the moon, or, hey, this earth that you're standing on is the earth, that moon that you're staring at is the moon, that sun that, you're staring at when you're not, when you're stupid and you don't know not to stare at the sun. Those are things that probably someone may understand more intrinsically than concepts like surgery or like quantum mechanics, which is what my article is about. So it could be that even though it's something that's well replicated in a 3D environment, it's not something that we needed a 3D environment to understand.
For sure. I think that VR it's almost a solution that's looking for a problem at the moment. Mm-hmm. You have to look really, really hard to find something where VR would benefit. I don't think that VR is true embodied cognition anyway. The level of dexterity that's required is probably far lower than using hands-on activities. So one thing I did want to note, though, is that, as I said, there was no difference across the 3 conditions in terms of the improvement in knowledge or the learning. But if they actually enjoy doing it more, isn't that a good thing?
Yeah.
Yeah, but that goes back to the point that I was saying. Yes, they like doing it more, but it's because it's novel. And if the novelty puts a higher cognitive load on them and gets in the way of them learning, then is that engagement really worth it?
Yeah, and also the novelty is obviously because VR is a new thing, and that's going to decrease over time. So enjoyment will decrease as well as they become more widespread, or that students actually get used to them. One other thing that I noted is that I saw a video that showed how the VR system worked, and to me, it looked backwards. And that's because the moon phases are upside down in the southern hemisphere. Just another example of northern hemisphere centrism and imperialism, quite frankly.
Interesting.
Guilty as charged.
We did an episode last summer that was all about having fun in the summer and like summer activities. And of course, one of our hosts on that episode was in New Zealand. And it didn't even occur to us that we were asking her to talk about summer topics in July, and it wasn't summer for her.
Very, very cool.
I'm wondering how many of our viewers here in America are going to be really confused when Duncan spelled out physics and said ZZ.
Oh, really?
What is that?
Sorry, I didn't realize that. Yeah, ZZ, as in ZZ Top.
There we go.
One thing I just wanted to finish on is, like, obviously the title of the podcast is is useful science. So what's useful about this? Well, two things that I could come up with. First of all, that good education doesn't necessarily come at a cost. Okay, you don't need to spend thousands on VR equipment in order to teach these concepts. You can just do it with a ball and a stick or something like that. And secondly, if you are trying to educate someone who isn't keen, you could try VR, because at the moment the novelty is there. They might enjoy it more. They might have better outcomes as a result.
Great.
Well, that's a great lead-in to my article. So my article is less of an actual scientific experiment as it is a description of a computer game that teaches physics. But one of the barriers they had for developing this game was Jacob Sherman is the physicist behind it. And it says right in here, I thought people would be absolutely fine playing something that was similar to solitaire and flat and boring. But he found that, so he developed this flat, boring version of Quantum Moves at first and enlisted some people to try it. Only about 10% could even get it to open. And then no one finished the game. Everyone hated it. So, a crucial importance there is if you want someone to learn, it has to be engaging. It has to be fun for them. So this is, my article is Quantum Games Aim to Demystify Heady Science. And it's a description of a video game called Quantum Moves, which is available online. So it's part of a umbrella project called Science at Home. And you can just Google Quantum Moves, open it up, and play it whenever you want. But the idea is that it teaches quantum mechanics in a way that is not only engaging, but gets the learner to think in a quantum way. So usually if you look at quantum physics or, if you look at like a picture of an atom, it looks like a little solar system. And I know I'm probably the only one here who would think of this, but you're thinking quantum. Oh, okay, so we got to think about this in terms of Scott Bakula, Quantum Leaps, 1980 science fiction. Pretty different. So the premise for that show was he would make a quantum leap from one person's life to another person's life, whereas quantum physics deals with the jumping of electrons from energy shell to energy shell. So, going from high energy to low energy or low energy to higher energy. But that is even different than quantum mechanics, which is, I'm probably not going to be able to explain quantum mechanics, but it's figuring out the mechanisms of how quantum physics works. Does that sound good enough as an explanation?
It sounds good to me.
Can you tell us more about the game?
Yeah. So the game, instead of representing atoms as little solar systems, makes it looked like a U-shaped curve and liquid-like waves moving through this. So in these games, the people playing them have to drag atoms through this space, and they have to anticipate where these atoms are going to occur. So one of the aspects of quantum mechanics is that an atom isn't in the same place all the time, and it might be in different places, and it's almost like a little bit like Marco Polo. So you have an idea of where the atom is, but you can't actually see it. And then when you measure it, it's like if you are Marco and you open your eyes and now you see where all the people you're trying to tag are. But they could have been in a number of different places. So for these games, you have to get people to understand that things might not be in one place, and they have to sense where in a physical space these atoms might be. And the whole idea behind this is that you can not only teach physics to people who might otherwise say, no, thank you, good day, sir, but it's also crowdsourcing potential answers to physics problems. So one quote from the article is, there was a German taxi driver with a 9th grade science education who had reformulated the whole process of quantum tunneling through playing this game. So people can help understand this. It's just a lot of people are never going to get to the point where they take physics or understand physics the way they teach it in college.
Oh, that reminds me of folding at home.
Yeah.
Mm-hmm.
Yeah, so I have a PhD in neuroscience, but I never got far enough in math to take enough physics classes to even get a Bachelor of Science. So my undergraduate degree, I have a Bachelor of Arts in biology, which, yes, that is ridiculous. And even before, when Duncan was saying, oh, Jaime, you're a neuroscientist, you probably know something about cognitive load. Well, sir, you would be mistaken. I do not have anything to bring to that conversation because that is something that's outside of my wheelhouse. I think for our audience, it's nice for them to realize that even if you have this somewhat artificial title of smart or expert in one section, that doesn't mean you understand things in a spectrum of other areas. But also, as this Quantum Moves open source video game shows, you can have a 9th grade education and be a taxi driver from Germany and still be able to solve problems in physics that experts might not be able to see.
Have you played the game?
I have not played the game.
I played the game actually. I downloaded it and I tried to see if I could use it to teach my students. I will be honest, I'm sorry to be a party pooper here, but I do not think it actually conveys any real information about quantum mechanics, nor do I don't quite see how students can learn quantum mechanics from this. I was actually very excited once I read the News and Views article, the one that the interview that you sent, that I was like, wow, okay, this actually might be very helpful. And then, so this was the Popular Science writing article that accompanied a paper where they showed that it can actually be used to solve a lot of problems in quantum computing. And that article, it's really impressive how they were able to use the data from people moving the atoms around in order to get a good first starting point. So when you want to do optimizations, then it's very useful to know where to start the optimizations. And so they were able to get a nice heuristic as to where to start the optimizations, and then their optimizations did very, very well. But in terms of the actual understanding of quantum mechanics, maybe it's because I've been doing quantum for so long and I have a different picture of it. But when I was moving the atom from one spot to the other, it was like moving a bucket of water. And I did not think the idea of a wave function and of a probability wave moving in space wasn't really conveyed. There's a lot of deep physics going on in the actual simulation, but I could not see how a student might have learned the physics by doing this game.
Yeah, well, that's one of the last things. They finish up this article by saying quantum moves doesn't focus on increasing a person's understanding of the details of quantum physics. Instead, it is trying to get them to learn the process of thinking about quantum oddities. And then they can merge it with their everyday experience and intuition and get a more intrinsic understanding of quantum effects than someone who wouldn't play the game.
Yeah, so one of the biggest things that I was trying to understand as to why they thought that it would be helpful was because one of the biggest hurdles for me in understanding quantum mechanics was the idea of a probability wave. That, I mean, I won't go into it. But basically, as Jaime was saying, it's the idea that any object is actually expressed in terms of its probabilities rather than its actual position. And in playing the game, the probabilities were conveyed in terms of this liquid that was moving around in this bucket. And it was very easy to lose the understanding of that as a probability. And there was nothing there that made it seem like a probability.
That might be something that our listeners now could intrinsically get more. The idea of trying to predict probabilities and thinking of things moving in that way, because everyone at home right now is trying to estimate how to keep themselves contained from this pandemic we're dealing with. So that's something where you could imagine maybe understanding quantum oddity would come into play in an everyday life, or perhaps our whole world is going to be changed, because who was thinking about predicting things by probability in November?
I was just quickly going to say, I think the game itself might not be useful for teaching the details of quantum mechanics, but it might be a fairly good approximate model for how this stuff works. So I think it's the Bohr-Rutherford model, the sort of solar system model of the atom.
Is the Rutherford, yeah.
Yeah, it's a decent model that we can all understand, but as we now know, it's pretty much incorrect. Whereas understanding the probabilities of quantum mechanics is very, very difficult. So if we can just help people along a little bit to understand the differences, I think that can only be a good thing.
Well, and the article also discusses how an aspect of this was coming up with a game that could teach physics, but also coming up with a game that was engaging. And so they had to scrap the first version of the game because it was boring and hire a team of game designers to come in and say, okay, well, we're going to do a score system and we're going to make levels of increasing difficulty and all these things that they had to tack on in order to make this something that people actually wanted to do. In a lot of ways, yeah, this article really reminded me of the book Three Body Problem. Has anyone read that?
Heard about it.
I have.
Yeah. So, and that also from Duncan's article on using VR, I thought about that book as well. So the premise of that book is that there is a online game community where you put on a VR suit and you join this community and you're trying to figure out how to predict when this alien planet goes through a stable era where you know when the sun's coming up, the weather and gravity are all normal, and a chaotic era when everything's just sort of like Alice in Wonderland. The sun comes up and then it goes back down and it's crazy. And spoiler alert, it's tied into an alien species and there's mystery and it's a pretty good novel. But they were using this platform and the three-body problem, which is, I guess, something physicists think about, to crowdsource solutions and also to expose an entire population of planet Earth to a concept that would have otherwise been foreign to them.
Yeah, the reference to the three-body problem is, so it actually has nothing to do with the real three-body problem, but it is a problem that cannot necessarily be solved. And so in the book, he creates a computer out of humans and has to numerically solve it. So it's an interesting book. I would recommend a read if you, especially in these days of quarantine.
Yeah, we got lots
And
of time.
also, it's like they're crowdsourcing the answer. No one actually physically builds a human centipede style computer. I don't want our audience to go get the book and then be sad when it's not absolutely horrific when somebody builds just bioterror builds a computer out of humans. It's more like they use a whole bunch of people to answer a problem.
Have any of you seen the movie Drumline? Have you heard that movie that came out, I don't know, probably 10 years ago about drum lines?
That's a hard no for me.
I teach drum lines, and that movie is dumb.
What are drum lines? Sorry.
It's like in a marching band, the percussion section.
Oh, sure. Yeah.
Drums. Yeah. But anyways, coming from a perspective of having knowledge in that area, the movie's dumb, and it gets a lot of stuff wrong. But I know that it wasn't made for me. And I feel like probably it captures some essence of it, or some feeling of what it's like to be in a drum and what it's like to be around a drum line that helps an audience understand it a little bit.
What did you think about Whiplash?
I have not seen Whiplash, but I've seen some of the famous scenes on YouTube, and I also thought they were dumb. Like in particular, there's like a scene where he's doing the big solo at the end to the caravan, and like while he's soloing, the teacher guy is like almost conducting him, like kind of indicating what he should do next, which is completely insane and would never happen. But I suppose it captures like the feeling of being a musician under those sorts of stressful environments in a way that helps people understand a little bit what it's like to go through that experience of studying music in an intensive environment, like what a conservatory would be.
But I've heard that jazz musicians just hate that movie. So many inaccuracies.
Yeah, I'm not a jazz musician, but I haven't seen it, and it does look kind of dumb. But again, like dumb from my perspective, and it wasn't made for me. Or if you're a cheerleader watching Bring It On.
Well, that's just a great movie all around.
Yeah, Duncan
Bring
is
It
correct.
On is great.
I don't know. I'm not a cheerleader, but I do love Bring It On.
Yeah.
So, Jaime, did they actually look? Did they study at all the effectiveness of this game in teaching these concepts?
They did not. So the only measure of effectiveness they have is how many people have downloaded it and are using it. So let me see if I can find that. After studying the trajectory of about 12,000 game plays executed by 300 players.
So in the Nature paper, they said it has been played 500,000 times by roughly 10,000 players.
There you go. So that's your stats right there. That is the only measure of success they really have for it is how many people have wanted to play it. And the article I linked to, it describes quantum moves, and then it goes on to describe other similar games. So it describes Gut Check, the microbiome game, and it describes Lab Escape, which is a physics-based escape room franchise. But otherwise, they go into the difficulty of designing it more than they do its effectiveness at teaching quantum mechanics to either a physics audience or a general audience. And, I read a lot of articles trying to pick one that I thought would be useful but also interesting for our audience. And it seems like, teaching physics, there have been a number of articles going back to the 90s about how do we do this? And can we use games to teach physics? Can we use science fiction to teach physics? Can we use superheroes? How can we get people who even signed up for a class on physics to understand the concepts that are necessary for becoming a physicist?
Who was it that said, if you think you understand quantum physics, you don't understand quantum physics?
Sheldon Cooper?
No, who was it? Feynman. Must
It
have been
was probably
Feynman.
by the time Feynman came around, we had a good understanding of quantum physics. It's probably somebody in the 20s and 30s.
Well, but I think the joke is that if you think you understand it, then you don't realize how much more complicated it is than you think it is.
I have a book
Sounds like it could be Feynman.
that I read to my son called Quantum Physics for Babies.
Oh, fantastic.
Yeah.
And yeah, it is. It's Chris Ferry is the author, and it's a whole series. So they have, we have general relativity for babies, Newton's laws for babies, optical physics for babies, rocket science for babies, but they also have blockchain, evolution, statistics. But quantum physics was sort of his first or his flagship book. And at the end, it describes quantum physics in terms of, a little solar system, and this is an electron, it's jumping up, it's jumping down. The last page, it says, now you are a quantum physicist. And maybe that sums it up. That book breaks it down to this for children. My son's not even 4 yet. And then it's like, oh yeah, now you're a quantum physicist. It's like,
that's amazing.
There might be a little more to it than that.
That's cute, though.
So, Cameron, both of us are right. It was Niels Bohr that said it really long ago, but Feynman was the one that popularized it.
Oh, there you go.
I have a huge celebrity crush on Niels Bohr.
He doesn't have the sex appeal of Feynman. I think Feynman was supposed to be kind of a womanizer, right?
He used to work at a strip club. He used to do his work at a strip club because it helped him concentrate, supposedly.
It helped him concentrate. I can't think of a more distracting place. Have you seen that there's a really fantastic photo from the 1927 conference on quantum mechanics? And it's
the Solvay conference?
Yeah, Solvay conference, that's right. Yeah, it's there's a great photo from that, and it's really the who's who of anyone in physics. So, but yeah, you've got Einstein sitting there at the very, very center, and everyone else surrounding. I can't remember who else is in it. Niels Bohr is in it. There's a lot of other big names at the time, but definitely Einstein is, squarely in the front. Everyone knew that he was a big deal at the time.
Well, shall we move on?
Yeah.
So the paper I wanted to talk about is called Molecular Insight into the Slipperiness of Ice. It was out of a team mostly based in the Netherlands, but also in Germany. So just to give a bit of a background regarding the slipperiness of ice, like we've all experienced it in some way or the other, unless you come from a hot climate. And in that case too, you probably have a little bit. And it's a good question as to why you would slip on ice, which is a solid, as opposed to other solids where you don't slip. And Faraday was one of the first people who started studying it in detail, and it was because it had there was a lot of connection to a lot of ideas in statistical physics that people were exploring back then. And he thought that it was because there was a layer of water that exists at the interface of the solid and the liquid, solid and the air. So in this case, the ice and the air. But people had measured slipperiness of ice even up to a temperature of minus 35 degrees Celsius. And at that point, you wouldn't expect there to be that tiny layer of water in the middle. So another explanation that a lot of you might have heard of is that once you put pressure on ice, the melting point of ice goes lower, and thus you're going to have a thin layer of water between the ice and whatever is sliding on it. The problem with that is that you would require an immense amount of weight. I think for an ice skate, you would have to have a metric ton of weight on top of the ice skate in order for there to be any measurable difference in the melting point of ice, or enough to facilitate ice skating. So the third explanation that emerged was because of friction. So if the idea is that if you start moving on ice, then there's going to be friction generated because of the movement between the person who is sliding and the ice itself, and that causes a thin layer of water to come about, and that causes people to slip. But you've all probably experienced this. Ice is slippery even when you're not moving. Even if you're just standing, ice can be very, very slippery. So a lot of people have been exploring the what exactly could be making ice slippery for a long time. And in this paper, Bart Weber and Yuki Nagata, who lead the research, they looked at a metal ball sliding on ice, and they looked at a huge range of temperatures from minus 100 degrees Celsius to 0 degrees Celsius. And they found that at the colder end of that range, the friction was high. So there is some element of friction to it, but the friction is not generated because of things moving. It's just that there is actually a friction, and the friction is because of temperature itself. And the friction decreases and reaches a minimum at minus 7 degrees Celsius, which is actually the temperature at which ice skating rinks put their ice, because they know that it is the temperature at which you have the fastest movement. Once you go between minus 7 and 0 degrees Celsius, then it really shoots up, and it's actually very difficult to skate on ice between minus 7 and 0 degrees Celsius. And they followed this up with molecular dynamic simulations, where they estimate that the water molecules, there's two kinds of water molecules in their simulations, where you have some of them bonded only to two or three other water molecules, as opposed to four bonds in the bulk of the ice. And as the temperature warms above a certain point, which they found to be minus 70 degrees Celsius, the proportion of the molecules with just two bonds starts to increase. So these molecules that have just two bonds, they act like rolling logs, which fall in place in front of a skater or an unlucky pedestrian to glide along that surface, and thus just push it on as you would imagine something being pushed on rolling logs. Does that make sense so far?
We're still talking about ice, though. We're not talking about liquid water.
So that's the thing. It is ice. Exactly. It is ice, but it behaves. So the way it works is it is elastic. And typically you would imagine any solid to be completely plastic. So if you create a deformity, then the surface carries that deformity. But in the case of ice, at that temperature range, the molecules actually fall into place, almost kind of like a liquid, but not exactly like a liquid. So it is ice, but it still falls into place, and it doesn't conserve its crystalline structure, because the molecules at that point only have two or three bonds. If you have four bonds, then you're kind of tightly jammed into place. But if you have only two or three bonds, then you can slide into that tiny little space in front of a skater, and thus you can roll on the ice molecules that have come into place. Does that answer your question, Cameron?
I think so. I guess I don't understand the difference between a solid and liquid when it comes down to it. Because if we're talking about molecules moving around, I guess I don't understand how that's not a liquid.
Yeah, so that's a really good question. I guess the main idea is that if it's still a solid, so if you think of an elastic substance kind of like a rubber ball, right? If you cause a depression in a rubber ball, it'll still pop back into place.
Yeah.
And so it's similar with the molecules on ice, that the molecules will move, but they can't completely move freely. They can move just enough that there can be a deformation. And then you can move along that deformation, if that makes any sense.
That's really interesting, actually.
Yeah, I follow that. Okay. Yeah.
Yeah, but the ice is elastic at that point in only a very small regime of temperature, or at least to some extent. It doesn't, once you start going to warmer than minus 70, then it starts becoming more and more elastic. And then once you get to minus 7 is when it is elastic enough that you can actually skate.
Right. And then you said as you go above minus 7, it gets slower.
Exactly.
So that kind of debunks the idea that it's water, because if you go above minus 7, you'd think you'd have more water and it would be getting more slippery, but that's not what's happening.
Exactly. Yeah. So it's not, of the three hypotheses that I had stated earlier, that shows that the water part isn't entirely the story. There might be some element of it, but that is not the dominating effect, especially when you're talking about ice skating. The second hypothesis that I've talked about, pressure melting, we have long known that cannot be the case, because at that point the pressure does not change the melting point that much. And the last one is the friction melting. And so what this paper talks about is how the friction varies smoothly with temperature, and it is not because of a sudden transition from water to solid. It's not because the friction is generating heat and melting the water. It's because the friction itself is changing over time.
I think it's like putting aside the fact that as an Australian, I find it very difficult to relate to this idea of slipping on ice. I think it's. I saw snow for the first time when I was about 12, and I don't think I've ever stood on ice in shoes. I think I've only ever ice skated. Anyway, I think it's really interesting, Avaneesh, that you know, originally in describing this, you've been talking about the molecules have 3 bonds, 4 bonds, and then 2 bonds. And, as someone who is not in that world, I would originally find that explanation a bit, I don't want to say lackluster, but not enough. I just don't understand it because I'm a bit of a dummy. But what's interesting is that when you start explaining it in terms of rolling logs and the elasticity of a rubber ball, that makes perfect sense to me, right? Because you're using a metaphor to describe these really complicated topics. And that's so important in science communication, really, really important, especially when you're dealing with kids like I do. You always have to rephrase things in terms of things that people will understand. And so for me personally, this idea of rolling logs, molecules that sort of move around but then bounce back elastically makes a lot more sense to me. So did you come up with that metaphor, or was it in the paper?
No, it's in the paper.
Oh, okay. I was going to give you credit for that, but now you don't get it.
Yeah, it helped me too, that metaphor.
I am familiar with ice. I lived in Boston for close to 10 years, and I've been skiing and snowboarding since I was like 4 or 5. I live in Maryland now, so we didn't have a lot of ice this winter, but I deal with ice in my daily life. And the explanation made sense, but also if you understand ice, then you don't need anyone to explain why ice works that way. Like if you've fallen on your ass before, you very quickly learn how to walk on ice.
If you think you understand ice, then you don't understand ice.
I love this. This was published in 2018, right? I think that's what it says.
Yeah.
I love these kinds of stories where, like ice rinks have known probably for decades, maybe 100 years or whatever, that the optimal temperature is -7 degrees, but it took us until 2018 to figure out why. Like we can get these kind of intuitive observational understandings of things, and we can achieve pretty incredible things as a species, but actually understanding why this stuff or how this stuff works is so much harder.
I remember I read recently, and by recently I mean like 5 years ago, they had just figured out why tea kettles whistle. So how long have we been making tea and using that whistle to know it's done, but they never knew why it worked?
Isn't it just because the steam expands?
Well, I guess there's more math to it than that.
Yeah, something to do with rolling logs and molecules and bonds.
Right. Have any of you guys ever played the horrible, cruel game where you put salt on someone's skin and then you put an ice cube on top of it and rub it on them?
Mm-hmm.
No, what happens?
It burns. It
Really?
is painful.
Oh, I can't wait to try this.
Yeah.
It was a form of torture that was used in colonial India.
Oh, I better not then.
Wow.
Oh, it was a game we dumb kids used to play growing up, which just makes me feel even stupider. It was like, I'm a younger sibling. It's something you would trick your younger siblings to do. Now, of course, we'd have it for like 2 seconds or something, not to the point of torture.
And why does that happen?
Yeah, do we know how that works?
Yeah, so that's actually my understanding of it. Again, this is folklore at this point. I don't know how tested it is, but impurities actually do significantly change the temperature, the melting point of ice. So that's why when there's a lot of ice, the municipal bodies will go and scatter salt on the roads, because that brings the melting point much lower, and the water does melt. And so in those cases, when you put the ice with salt on your body, the layer just next to the ice will have melted, but then your skin will have frozen with the remainder of the ice, is my understanding, because the ice is still colder than the melting point of the water that has melted and gone into your skin, I guess. I don't know exactly what it is, but it sears into your skin.
Wow.
And I mean, I have done pain testing before where we used noxious cold as a pain stimulus. So at a point where the temperature becomes cold enough, your body reacts as though it's burning. So there's a different pathway, but it's a very similar sensation from someone who's experiencing it. So they've developed electrodes to mimic this if you're trying to do pain testing in a lab. So if you're trying to figure out if an analgesic works or not, and you want to make someone in pain without causing any actual damage, they'll use a temperature probe to replicate a lot of pain that isn't going to leave a mark.
So, Avaneesh, can I ask, what would you say is useful about this?
I know, absolutely. I mean, obviously now we understand a bit more as to why ice is slippery and why -7 degrees Celsius is the temperature that it is the most slippery, and that's when you can go fastest. In terms of practical utility, I don't know if it introduces much that we don't already know based on having dealt with ice for the last whatever number of thousands of years. But I think it gives a good picture as to how we don't often understand the molecular mechanisms behind certain things happening. And there are many different explanations that might come in, but once you go through a rigorous testing, then a lot of the intuitive pictures of how something that even in our daily life seems clear break down, and you realize, oh, it's not just quantum mechanics that's really complicated. It's also things like slipping on ice that we may have an understanding of practically, but in terms of understanding the molecular mechanisms, it takes lots of years, 200 years in this case, of scientific inquiry to be able to elucidate.
What I could see, like for you as a human being, this might not help you learn more how you can walk on ice. I mean, even talking about ice brings me back to many memories that have taught me how to navigate on ice, and all of them painful. But this would be really helpful if you're trying to develop a tire that doesn't slip, or a new kind of material for Arctic environments or cold environments. So it might not help us where we are today, but it might help us understand how we can navigate it better by developing different materials or maneuvers around it. Since falling on your butt is very painful, but crashing your car because your tires don't grip the road, that's even more painful.
Absolutely. I think this is probably the perfect opportunity to bust out the amazing cheerleader chant from the seminal film Bring It On, which goes, "Brr, it's cold in here. I said there must be some Tauros in the atmosphere. I said." It's the one about ice. You remember that one?
Nice.
It's all coming back.
Duncan, Niels Bohr has competition. It was the best quote.
Oh, dear. It's a good film. I'm going to rewatch it.
Well,
Cool.
Let's wrap things up. Well, that's our show. Thank you so much for listening. As always, we appreciate your feedback. You can email us at podcast@usefulscience.org. You can follow us on Twitter @usefulsci. You can find our subreddit /r/usefulscience. And that's where we will post the episode there, so you can comment on it if you want to have some back and forth with us. We also have a Facebook. Just search for Useful Science. And lastly, you can sign up for our newsletter on our website, usefulscience.org. I want to thank our fantastic editor from Moorhead Planetarium, Vivian Lee. I want to thank the composer for our new theme music, Solomon Krause Imla. My name is Cameron Spencer. You can follow me on Twitter at Usonic. That's EUSONIC.
My name is Duncan Bell. You can find my podcast, Physics Twist, on iTunes or wherever you like to get your podcasts. I'd also like to say, given that now a lot of us are going to be locked up inside with kids, the company that I work for has actually produced some really great resources about free science experiments that you can do using, say, things you might have in your kitchen. So if you go to physicseducation.com.au, that's FIZZICS education.com.au, you'll find a lot of great resources there. Thanks.
I am Jaime K. Devine. You can follow me on Twitter at JK_Devine. And I will probably be going to physics education so that I can find some more experiments to do with my 4-year-old who is driving me crazy at home.
Perfect.
And I'm Avaneesh Nadler. Thanks a lot for listening and stay safe, everybody.
Thank you so much for listening. I hope you have a very useful week.